at Edinburgh and Cambridge. Before doing any mathematics, Maxwell first decided to understand Faraday's work and intuition, a decision that proved very fruitful. Faraday had inspired Maxwell to think of electricity and magnetism in terms of field lines, just like water flow. There are two key concepts, divergences and flux, used in fluid dynamics. Divergence at any given point is a measure of how fluid spreads out or comes together at that point. Curl, as the name suggests, measures the rotation or twistness of a fluid at any given point. The first paper Maxwell wrote on electromagnetism was titled On Faraday's Lines of Force, published in 1855. Merely as an analogy, Maxwell proposed that electric and magnetic fields could be thought of as incompressible fluids. A key property of an incompressible fluid is that its divergence is zero. This allowed Maxwell to immediately write down the mathematical expression for the behavior of magnetic fields. The divergence of the magnetic field is zero. This is the first Maxwell equation. The interpretation is that, unlike electric fields, there are no positive or negative magnetic charges that could act as a source or sink. Magnetic poles always come as a pair. Since the electric field has positive and negative charges that can act as a source or sink, the divergence of the electric field is equal to the charge density. This is the second Maxwell equation. These two equations are also called Gauss's law for electric and magnetic fields, though Lagrange was the one who first wrote it. The main limitation of this fluid analogy was its inability to explain the interactions between electric and magnetic fields. It took him another 5 years, along with insights from another great scientist, Lord Kelvin. Kelvin was an advocate of the vortex theory of the atom, which hypothesized that an atom was a vortex in the ether that pervades space. Kelvin suggested that these rotating vortices could serve as a model of a magnetic field. Maxwell found Kelvin's approach particularly attractive and took it seriously, though it might seem bizarre from today's perspective. He began with a model in which the whole space was filled with a vortex tube whose velocity represented the strength of the magnetic field. But there was an immediate problem. These rotating vortex tubes would experience friction, causing them to lose energy. Maxwell adopted a practical solution by inserting ball bearings between the vortices, which he identified as electric particles. When these ball bearings are free to move, they carry an electric current. In conductors, these electric particles are free to move, whereas in insulators, they are fixed. In 1861, he published a paper titled On Physical Lines of Force, with these mechanical models. In that paper, he had a slightly different version where hexagons represent the vortices. The ball bearings are current-carrying particles. Remarkably, this model could explain all known phenomena of electromagnetism. In this diagram, the change in the speed of the vortices corresponds to the change in the strength of the magnetic field. This would cause the ball bearings to rotate in response to the changing speeds of the adjacent vortices. Since rotation corresponds to the curl, we get the third Maxwell's equations. The curl of the electric field equals the change in magnetic field. Now we are left with the final equation. For this, let's consider this Maxwell's mechanical model. Trust me, this is the last one. In the center, we have an electric current. The electric current forces the vortices to rotate as an infinite series of vortex rings about the wire. Correctly, the magnetic field lines form circular loops about the current. This gives us the following relationship. Curl of the magnetic field is proportional to the change in the electric field. Again, using these mechanical models, Maxwell introduced a correction term called displacement current, which gives us the final equation. Curl of the magnetic field equals the change in the electric field plus a current density. These molecular vortices were modeled to be elastic objects whose disturbances could be computed. It was then a straightforward calculation, and to his amazement, the velocity turned out to be equal to the speed of light. In a single stroke, then electricity, magnetism, and light were unified. While Maxwell was greatly inspired by these mechanical models, over the years, he slowly started losing confidence in them. Finally, in 1865, at the age of 34, he presented a monumental paper titled A Dynamical Theory of the Electromagnetic Field, where he retreated from all the specifics of the molecular vortices model.
I am Butch Loxon.